Next speaker is Jaime Fernández. It's a pleasure to have him. He's a NumPy core developer. You know that library that's behind everything we've seen today and yesterday? So he knows how it works, which is kind of amazing to me. So please welcome Jaime Fernández.
Thank you. So thanks for having me. Let's see how this goes. We're going to talk about NumPy indexing, which is not like the sexiest of topics, one would think. But well, I'll try to make it a little bit interesting. Before we start, just do a show of hands. How many of you are NumPy users? Okay, cool. That's
Could
nice.
be all of you.
Now, bear with me one more minute. How many of you know what fancy indexing is? Okay, not that many. And I suppose that then if I ask you about orthogonal indexing, there'll probably be no one that knows what it is. It's good. I mean, you'll at least know that they exist by the end of today. So I did a very early version of this talk about a year ago to the San Diego Python users group. And we did the same show of hands. And in a room full of about 50 people, I think there were 2 hands raised. And well, it was an interesting experience, but I lost them really, really soon. It's like 5 minutes into the thing. It was mostly blank stares into the void. But well, we went through it. You should do better. I'm hoping that you'll you'll get lost a little later if you do. Now, the thing is, there were a lot of people yesterday saying that what they're doing is not rocket science, or now this is not that hard. This is some quite difficult and confusing shit, quite honestly. And it takes a lot of banging your head against it until it starts making sense. So if you don't understand how something works, or if you're confused, it's normal. We've all gone through that, and it gets better with time. That's the most I can promise. So as I was saying, there's fancy indexing, there's orthogonal indexing. Fancy indexing is the way that NumPy does multidimensional indexing. And then orthogonal indexing is the way that just about every other library out there that has to index multidimensional arrays, that's what they use, right? So it's NumPy and everything else. And everything else is typically newer and more modern. Right, so it sort of gives the idea that maybe NumPy is like the bald guy with a ponytail at the disco, right? That's still going hard 20 years after he should have left. And maybe it's time to say, well, I mean, we're wrong, and we should, you know, follow the trend that everyone else is following. The interesting thing is that at least some of those libraries that implement orthogonal indexing are built on top of NumPy, and they use fancy indexing to implement orthogonal indexing, right? So there maybe there is a case there for, hey, really, fancy indexing is a superset of orthogonal indexing, so it's cool to have more functionality, even if it's at the expense of some complexity, right? So, and I'm gonna try to sort of defend that stand, but I think I'm gonna fail at it, and you'll see why. So, well, but don't let me get ahead of myself. What does make sense if you have several libraries implementing a functionality that depends on a NumPy functionality is to try to push that functionality upstream. You don't want to have 6 different implementations of the same thing that start diverging slowly one from the other and makes things more confusing to users that find that this library that does this. Yes, that tiny slightly different way, that's bad enough to throw all your understanding of how the whole ecosystem works together off. So about a year ago, there was this discussion that started in NumPy world about how should we make access to this orthogonal indexing, whatever that may be, and again, you'll find out soon enough, available to other packages, and actually how do we implement it in NumPy and make it available. And we were having this very boring discussion on, well, you know, we do it like this, but that. It was mostly boring. I mean, it was like a completely uninteresting unless you're really involved with this discussion. And all of a sudden, it turned into and it was like a mob with torches going to the castle to kill the monster in the movies. It was like, I mean, the the rage, the hate that people had for fancy indexing, that sort of popped out of nowhere was, to me, it was a big surprise because I'm a big fan of the thing. I'll admit that. But yeah, fortunately, we calmed things down. I learned a thing or two about the social dynamics of open source communities. There were other good outcomes of that. I think we reacted pretty quickly to that realization of how upset people were about fancy indexing. I'm echoing, right? I'll stand back. And I think that within a day or two of that first outburst of rage, we had like, actually I wrote it, we had like a canonical Python mockup of what would orthogonal indexing look in NumPy. And not more than 2 months later, there was like a proper C implementation. There's an app, a NumPy Enhancement Proposal, outlining how and why that should be done. But the thing is that a year later, nothing else has happened. We had this outburst of rage, we had this outburst of coding, and then everything has quieted down and no one is like talking anymore about this. So one of the main reasons that I'm here talking to you is because we want to hear from users, right? We are like a not so large community that participate actively, and there's a strong sensation that we may be missing what people out there really are using things for. So if any of what I tell you today resonates with your experiences, if there's something you hate, something you like, something you are indifferent about, find some time, find me anywhere during the rest of the day. I'll leave my contact details somewhere. Yeah, but I would mostly, the main reason for this, aside from educating you and getting a free pass to the conference, is to get feedback from users, okay? So, yeah, with that out of the way, what I would like to do is to walk you through how indexing works, right? And from the background that I've told you, it's not going to be a very good trip for fancy indexing. I mean, we're going to talk a lot of shit about it. I'm mostly going to focus on the bad parts, right? But because that's going to be the center of the talk, before we do that, I would like to also highlight some of the nicest things of fancy indexing. I'm very partial to this because 4 years ago, I didn't know that NumPy existed, right? And of all the things in the world that can make someone fall in love with a library, it was fancy indexing what caught my eye in NumPy, right? So there's a bunch of imports. I'm using Python 3.5 because if you use Python 2.7, they look bad at you at these conferences because we should all be switching to 3. But yeah, behind the closed door of my house, I use 2.7. I'll admit that. I'm using a development version of NumPy. I can give you a link to the pull request that this is built from. I doubt that anyone is going to go through that trouble, but this is basically the pull request that implements the future of NumPy indexing, right? So we'll see some things that you will not see with your stock. You just use Anaconda as I'm doing here, and you use NumPy, I think it's 1.10, that's publicly available now. You will not get some of the same results, or you will not be able to see some of the things that I'm going to do here. But yeah, that's that. And since they've given me a stage, I'm going to show you a picture of my daughter. This is Gabby. This is about 10 million pixels. It's black and white because it's easier and it's also trendier. And we're going to transform this image. At the time that when I fell in love with NumPy, I was working for Hewlett-Packard. We were doing printers, and there's a lot of image processing there. And one thing we did a lot was to what we call linearize an image, which basically means that you have your colors, well, yeah, each pixel has a value that ranges from 0 to 255, that it's supposed to represent colorfulness or darkness in this case, right? But when you're going to print it, you want to turn that into how much ink you have to put down there. And colorfulness and amount of ink are related, but it's not a linear relationship. And if you don't modify that, what you get printed is not what you were seeing in the screen. So you have to apply a nonlinear transformation to the input values to get something else. So typically, in image processing, you do that with a lookup table. Okay? Basically, because typically images are encoded as unsigned bytes, you have 256 possible values. So you create yourself an array of 256 values. This basically says that, well, this is transforming the first, 10, 12 levels to 0, okay? But yeah, it's basically an array of 256 integer values. And this is easier to see if we plot it. We're basically modifying things so that dark colors are going to look darker and light colors are going to look lighter, okay? Yes, this sort of burned look to an image. If you wanted to do this in Python, you would typically do something like this. And here, right? You basically iterate over the rows and the columns and the image. For every pixel in the image, you extract the value, you look it up in the lookup table, and then you write it to your output file. And you keep doing that 9 million times, 10 million times, depending on the size of your image, right? I was afraid of doing this. Let's see how it works. Let's time how long does it take. And we're probably going to have an uncomfortable silence before it finishes. Come on. It should take about 3 seconds to process that image, which turns out to 12 or something like that here. Yeah, 336. Now, NumPy lets you do this in a blink of the eye by basically saying, well, yeah, down here, saying, let me take care of the iteration for you. You're going to iterate over all the pixels. Just throw the image inside the square brackets, which is the indexing operation, and I'll take care of that. We have the lookup table, we have the image, and the same thing happens 200 times faster, if I'm not mistaken. Come on, yeah. 15, 3.36, it's basically 200 times faster. And it's a single line of code, and before I discovered this, I was living in a world of C++ libraries wrapped in Swift, and then you could use them in Python, but it was bad. I mean, no, and this was like, it opened my eyes and my life to a whole new set of I don't know, of experiences that I had never imagined, right? Just to see how this works. So we've basically ruined the picture, but it does what we asked it to do, so we should be happy. It looks better. Yeah, it's shit, but the lights are lighter and the darks are darker, so mission accomplished, right? And okay, so you've seen pictures. Victor Terron of PyCon Spain fame, he says that when you give a talk, you should try to be entertaining and well, I hope we've basically gone, that's all the entertainment you're going to get today. That's what I wanted to make clear. Now it's going to get boring, but you've been entertained, so keep that in the back of your minds. Yeah, so we're going to walk very quickly about how indexing works, mostly, and we're going to do it by dimensionality of the array being indexed, because it makes it easier to progress and see where things start going bad and when they derail completely, right? So we're going to get an array full of letters, right? It's just the alphabet. NumPy one-dimensional arrays are really very similar to Python lists, right? So if you index them with a single integer, you of course get the value at that position. J is the 10th letter of the alphabet, so if we index with 9, we get the 10th letter. You can also index with slices, and you get what you would expect. Everything starting at the third letter, and then every third letter. There's no big surprises here. We could go on to how slicing an NumPy array gives you a view and not a copy, but I'm not going to go there. There's slight differences, but it's not very relevant. And the interesting thing is that you can also use an array to index an array, right? And when you do this, it basically lets you grab a completely arbitrary slice. And in this case, how cute. Look, fancy indexing is saying hi to you. How could you not love it, right? All those mean people that want to get rid of it should be ashamed of themselves, right? And so we're going to go see how it works in 2D arrays, but I haven't really explained. I mean, the first example I showed you was an image. No, it was a one-dimensional array being indexed by a two-dimensional array, but it should fall here under indexing 1D arrays, and we are tiptoeing over it, right? Why not, right? I'm sure that there's a good reason for it, and that nothing bad will happen by not fully explaining that case. So let's go to the arrays to find out if that's true. One small, this is really a Python explanation. This is a very stupid class that simply shows you what you're using to index that class. It just prints what gets passed to the getItem magic function. As you could imagine, if you pass a single value, what you get inside the function is that value. Python has, and this is not just about indexing, but when you start putting commas in places where they don't belong, Python typically wraps that in a tuple, okay? So this kind of quirk of Python is what NumPy uses to index multidimensional arrays. When you index a multidimensional array, NumPy is expecting to have one index per dimension. And there are ways around it. We'll see that very quickly. But basically, rather than using square bracket, square bracket, square bracket, square bracket, as you would do with a list of lists of lists, you put everything inside commas. Inside a single square bracket separated by commas. If you do the math, you're actually not saving any typing. So you're changing a comma and a space by a closing and an opening bracket. So there's really no saving anything. There are other reasons. I mean, and it basically looks prettier, right? Which is probably good enough of a reason. But yeah, let's see how NumPy handles two-dimensional indexing. We're still going with letters. I've added numbers so that it fits into a nice square array. And yeah, not many surprises if you use two integers to index that array. You get the value at the fourth row, fifth column. W, here it is, right? When you use a slice and an integer, and let's look, see what it gives you. Here it says, well, it gives you the contents of the third row, and from that third row, it gives you every second column, right? If you do not, if there are missing indices, it replaces them by full slices, okay? So, yeah, if you have less indices than dimensions in the array, you get basically more than that. Instead of every second, you get all of them, okay? You can do the same thing with the column. Now here there is an interesting point in that up there is not a row vector and this is not a column vector. They are one-dimensional arrays that have the content of that column and row vector, okay? But this is not. You've lost the dimensionality. When you use a scalar to index one dimension, that dimension is going from the output, okay? And this is important. And if instead of a slice you use an array, the result is basically the same. You're getting, for that row, those items, for that column, those items, okay? Yeah, they're the same results with slices or arrays. And there is then the case of what happens when you mix. You get rid of scalars and you mix slices with slices. And this is, and basically what you get is these rows, these columns, and we get the intersection. This is what orthogonal indexing is, okay? Is each index is acting on it's kind of a big name for a small thing. They also call it, some people call it outer indexing, but anyway, that's all there is. There's a lot of professors working on NumPy, and they seem to like the big words, right? So anyway, two slices do this. If you use a slice and an array, the behavior is the same, okay? If you use an array and a slice, the behavior is the same. So of course, if you use two arrays, you get something entirely different. Because why not? That should be actually red, light red, because that's a warning. And that's a warning that you only get if you use this pull request. Because basically, NumPy is telling you, you're going to hurt yourself. Don't do this, right? And we'll explain what that means. But yeah, that's the reason to use letters for the array. So I could say, right, what the fuck, without explicitly spelling it out. What NumPy is doing here is it's using those indices to get rows and columns, but instead of getting all the rows and all the columns, it's combining them to get a specific item inside the array, right? So if you look at this, like if you wink at it, what you're seeing is like really that behavior we saw at the very beginning, where the shape of the indexing array determines the shape of the output. I had a one-dimensional array that I indexed with a two-dimensional array, and the result was a two-dimensional image transform. Is not a small thing that only happens for one-dimensional indexes. That's like the core thing of fancy indexing. You get the same thing as the array you're using to index, and actually both arrays have to have the same shape. They have to have the same size, the same dimensions, because if not, they cannot work together. And of course, that means that if what I want to get is a two-dimensional output, all I need to do is use two two-dimensional inputs, right? So if I do twice the typing with the same warning, I can get the orthogonal indexing-like output, right? This is hard trying to convince someone that, see, orthogonal indexing is a subset of fancy indexing. You just have to do a little more typing. This doesn't really work out very well. I mean, people get angry when you try to say that. It's actually easier. And we have to go into another of those obscure features of NumPy that turn out to be super powerful. That's called broadcasting. And first, I'm going to show you that with a clever use of square brackets, I can actually get the same output with much less typing, right? And what's going on here? So basically, what we're doing is we're using an array that's actually a two-dimensional array to index the rows. It's like a column vector. And we're using an array that's actually a two-dimensional array. You might want to count those square brackets. There's two of them, so this is actually a row vector. If we put their shapes together, one has two rows and one column, the other has one row and three columns. When you give NumPy arrays that have different shapes and it's expected to do things with them together, it tries to broadcast them. What broadcasting means is that if one dimension is a 1, it will match any other dimension. Basically, that single row or that single column will be replicated until it fits 3 columns, okay? And similarly for this, that single row will be replicated until it fills 2 rows. So with only one dimension for each, you can create a 2-dimensional array. And the interesting thing is that you don't actually create it. NumPy has ways to access the memory, the small memory you have, so that it looks like a 2-dimensional array without you having to actually allocate that information. So when we get those 2 arrays that we have defined, that is one column and 1 row together, we get what we've already seen, which is that aside from a warning, you're going to hurt yourself, don't do this, you get the two-dimensional output that you were looking for. This is so typical that I haven't modified this like I should, that there is a function, NumPy ix underscore, that does this for you. You give it to several one-dimensional arrays, and it adds extra dimensions so that they will all broadcast together and do orthogonal indexing, right? And if you use this inside indexing, you get the orthogonal indexing-like result you were expecting. So this sort of kind of says, yeah, I mean, you can do orthogonal indexing with fancy indexing. It's a little annoying, right? You have to type a little bit more, but it's sort of there, right? If this is all the annoyance that fancy indexing was causing people, it would probably be dismissed as, well, you don't understand how good it is, so you don't deserve all the good work we've done for you, and go away. But unfortunately, it doesn't stop here. And like before, we had not fully explained how does the two-dimensional thing worked. Here we have tiptoed about the fact that when we were using a slice and an array to index, things were working beautifully well. We were having no problem there. And again, I'm going to ignore that. No one asked, so you probably have it all figured out already. And let's move on to 3D arrays. So we have three-dimensional arrays. We're not gonna look at the actual outputs because it gets really confusing. We'll just look at the shape of the output now. And basically we have three planes of 4 rows and 5 columns each, okay? Full of numbers. They're mostly irrelevant. And so there's 27. If you have int slices and arrays, there's 27 possible combinations that we could look at for a three-dimensional array. We're going to choose the fun one, where it all goes crazy, you know? And yeah, this is like a bad joke, a slice, an int, and an array walk into a bar. You won't believe what happened next. So I'm going to walk you through a few of these, and eventually they'll probably make sense. So we have a slice in the first dimension, so we should get 3 items on that dimension. We have a scalar on the second one, so that dimension disappears, and we have a 2-item array in the last dimension. So one would think that you would get 3 items in the first dimension, 1 gone, 2. And the shape is 3, 2, as expected. If you reverse the position of the scalar and the array, you're still having a slice of 3 items and an array of 2. You'll get different results, but you should still get a shape of 3, 2. And you do. If we move the slice to the end, now we're getting rid of the first dimension. We have 2 dimensions indexing the second. The slice is in the last, which had 5 items. So we're expecting a shape of 2, 5. And we get that. Again, if we reverse the position of the scalar and the array, it's still 2 in the first, 5 in the last. So we get 2, 5. If we put the slice between the scalar and the array, we would think that there's 2 from the first, a full slice in the middle, the last is gone, so this should be 2, 4. 2, 4, yes, right? And we do. So of course, when we get to the last example, where we would rightfully think that the first dimension is gone, we get 3 items from the second one and 2 from the last, we will get an output of 3, 2, and of course, we don't. Actually, it should have been 4, 2, not 3, 2. And we get the opposite, and a warning, you're gonna hurt yourself, don't do this, right? What's happening here? And the thing is, you have to keep in mind that this has to be a general functionality that works for up to 32-dimensional arrays with index with whatever crazy combination of slices, arrays, or integers you throw at it. So I'm going to show you with an example, a slightly more complicated example, how this works. And you might recognize those words from import this in the face of ambiguity. We'll see why this applies here. I'm going to use two arrays, the same two arrays, I think, as before, to index our three-dimensional array. And they have a 2-3 shape together, okay? So somewhere in our output, we're running out of time, you're going to have 2 and 3 close to each other. So the question is, what happens if I have those two arrays separated from each other, and I put a slice in the middle? We know that I1 and I2 together will create a 2-3 shape, but there's also a force coming from the slice in the middle, and the question is, where do we place that slice in the whole shape? And really, the only sensible answer is put it at the end. You could be tempted to say, no. There's only two. I mean, it should go between the two, right? Because one is indexing the first, the other is indexing the last. It clearly goes in the middle. You might expect that the output of this would be 2, 4, 3. But what happens if you're indexing 2 dimensions with a 3-dimensional array? So if the shape of the broadcast of our 2 dimensions is 2, 3, 5, we're going to have 2, 3, and 5, and we also have a 4. Where do we put the 4? Right? It's no longer clear that it should go between the two numbers. The only sensible thing is to either always put it at the back or always put it at the front. And the convention is that slice dimensions go at the end. They're actually called the subspace, right? Fancy big words for normal things. No? And this is perfectly good, rational behavior that it's a convention, get used to it, and move on with the rest of your life. But someone got clever and at some point decided, wait. If the slice is at the front, we don't want to send the slice to the back. We know that we have to have 2, 3, and 5 together, but the slice is at the front. Let's not put the 4 at the back. So there's a quirk in here where rather than having that 3 sent to the end, we put it at the beginning because all the slices are together and all the arrays are at the back. And this is very convenient because this is what makes those cases of a slice and an array work, but this is what fucks everyone else, right? Because it starts being surprising, because we are deciding that we want to guess what the user wants, right? We don't give you a set of rules and we say, hey, this is how it works, learn it, use them. We decide to figure out for you what you want. And when you get it wrong, hell breaks loose, okay? So this, and mostly just this, is what we are willing to agree that is broken in NumPy indexing, right? How do we want to solve it? And this is pull request 6075 has the answer to all things. We have added, or this pull request adds, 3 indexers to NumPy arrays. And this is basically, I think it's stolen from Pandas. Pandas has a couple of indexers that let you index with numbers instead of labels or something like that. The O, V, and L stand for outer or orthogonal, vectorized, which is the way that we call fancy, and legacy, which is this broken mess that it's our default indexing. So if this ever gets merged, let's just remember that our array has 3, 4, 5 as dimensions. You could index the orthogonal indexer with 2 arrays that don't match, but hey, 2 dimensions from the first, 3 from the middle, 3 from the end. You get the expected output of 4 from the middle, not 3 from the middle, of 2, 4, 3. No surprises here. You can have vectorized indexing, where despite having the slice at the front, the slice of 3 gets moved to the end, because in vectorized indexing, we put the the subspace, the slice dimensions at the end, and we first put the 2, that is the result from broadcasting those 2 indexing arrays. Oh, I'm over time. And we have legacy indexing, which is, well, I mean, enjoy your world of pain, right? Like, we're gonna mix things around, and yeah. And I'm out of time and out of cells in my notebook, so that's all I have to say about NumPy indexing. Thank you very much.
6,000 pull requests. That's quite a lot.
And growing. There's 1,000 open issues, which is more fun.
Wow. I don't know if that's good or bad. So, questions?
Everyone understood everything. It's great.
So I have a more general question about NumPy, since all we use NumPy in some way or another. And you get to see some of those pull requests and how the Git repository is working. How healthy you think that NumPy is now? Since we all depend on NumPy.
Can you turn off the recording?
No.
It's okay, mostly. I mean, there's things like this that are interesting, because when they happen and someone comes saying, oh, this is moving to the other way around, the other side of, and then we all think, oh, it's a bug, it's a bug, it's a bug. And there's a part of you thinking it has to be a bug because this is really weird. And there's also the part of you saying, I mean, people don't understand indexing. I'm supposed to do, even though I don't. So it's probably just another idiot whining about things he doesn't understand, and then eventually you find, oh, no, here, it's intended behavior. See, you're wrong, we're right. But mostly it works. It has little things. I mean, there's open issues from 6-7 years ago with segmentation faults happening when you do, which those are supposed to be really, really bad, but no one has solved them ever. So, but mostly it's okay. I mean, there's dark corners that you shouldn't go to or you'll hurt yourself, and we're trying to at least signpost them, so you don't hurt yourself, but it's mostly okay. I mean, it's getting better, I think. There's quite a healthy contribution, pool of contributors now, so I think it looks okay.
Sometimes when people ask me, because I've been coding in NumPy, with NumPy, so for some time, also in using Python for science, when people ask me how much the whole ecosystem has improved, and partly thanks to NumPy, so that we really have to thank all your effort, I tend to use that I used NumArray.
Oh. Yeah, and I mean, a lot of the weirdness in NumPy comes from the fact that there's something that, a minute and a half I have? Yeah, so there's a very, very, very strong and strict policy about backward compatibility in NumPy. There's a lot of things that are broken. I mean, it's like here. Indexing is clearly broken. It's tripping people. If you try to do elaborate things, we're going to put our leg in the middle and make you fall over. So the reasonable thing to do would be like, solve this, get rid of indexing. But you cannot do that, because there's always someone that has made this part of their workflow. There's the XKCD comic out there about the guy that used that when someone solves an issue where hitting the spacebar hits up the CPU, and the guy is saying, no, but that's part of what I used so that to turn caps on, because I have a temperature sensor on my keyboard, right? And you simply cannot, there's lots of things that are broken that you know that you should fix them, but it's like, we can't, because there's this guy that wrote code 15 years ago, well, maybe not that long ago, and that depends on it, and you can't simply break it. So it's keeping the balance between making it go forward and not hurting anyone from the past is a difficult thing. But I mean, it's fun though, I guess.
Thanks to speaker again.